This is the first class of this semester. I think you may have my syllabus, or you may read the syllabus from the internet. But there are three things I want you to notice. The first one is that we will have quiz, basically every Tuesday. So because today is the first class, so we don't have any quiz. But starting from next week, we will have a quiz in the first class on Tuesday. That means from 1:20 to 10 for 50 minutes. And especially on this particular day, October 24th, we will have 2 quizzes. The reason is that before that, we will have no quizzes because of some holidays. It's very hard to arrange a quiz. So that's why I have to put 2 quizzes together on the same day. Okay, so that is the first thing about quiz. The second thing is about the practice session. Our TA, he sits over there, in the back of the classroom. So Mr. Cho will be our TA, and he will hold the practice session. So basically every Monday from 7 p.m. to 8:30. So it's about 1.5 hours. And it's optional, so you are not required to attend the class. But I would encourage you to attend the class because the TA will demonstrate problem solving. Because that I will assign some homework, but you don't need to turn in the solutions. No, you don't need to. I just assign the homework. And the quizzes will be based on the recommended homework assignments. Okay, so you may have some problem when you try to work out the exercise, and so this opportunity is for you to ask TA to solve some difficult problem. Okay, so that is the and this is so I will not arrange any office hour for TA. Okay, so if you have any question, just come to this practice session every Monday. Okay, except yesterday and also these 2 additional days that we don't have any practice session. Okay. And the third thing is about the final examination. It's quite different from previous years. That the final examination is cumulative. That means that we will cover everything taught in the whole semester. Okay? So the final exam will be everything. Okay, so the range is that. Okay, so do you have any questions about the syllabus of this course? Okay. And as you well know, this course is English teaching course, so basically we will teach in English. Okay. Of course, you can ask me questions in the recess time. Okay, so I can speak in Mandarin or Chinese if I can speak. So, and you are welcome to raise your questions in any language, okay, as I say in my syllabus. So, and also I think I have to say, I basically follow the guideline of the textbook. But from time to time, I will give you hangouts, my lecture notes. Right? So for example, tonight I will send you the first lecture notes about the first section of chapter 11. So any further questions? Right? Oh, yeah, the final thing. I will announce my office hour it is some fixed time slots, but sometimes I have a meeting to attend, so I have to cancel my office hour. But I will send a notice to you through the ILMS system. So I hope you know the ILMS system. So please use. Right? Because that I will upload the lecture notes there, and of course you will receive the notice about anything that's been changed in the course website in the ILMS system. Okay, so any other questions? All right. So now, we'll start to. Talk about Fourier analysis. The first section is about Fourier series. Okay, it's about Fourier series. So we define the concept, and I assume, I think you all know that. Right. The first concept is about periodic function f defined on R. Defined on R means that the domain of this function is the set of all real numbers. So you all know the notation. So this notation is the set of all real numbers. So if there exists a positive number p, right, we call a period of f, okay, such that f of x plus p equal to f of x for all x is the set of. Okay, so that is the basic definition of a periodic function. All right, and a periodic function may have infinitely many periods. Okay, so p is just one of them. Okay, so there is one p. This one. So now, the smallest period p of a periodic function is called the fundamental period. Okay. So fundamental period is the smallest period for a periodic function to have. So that's it. So let's see a familiar example. Okay. Right. So define a function which is tangent function. And we know a tangent function can only be defined for all x such that x is not equal to integral multiple of pi over 2. So that it cannot be defined right, in the integral multiple of pi over 2. Pi over 2 is equivalent to 90 degrees, right? So we know tangent x cannot be defined. So we just define that the value of the function is x is 0 when x is equal to this point, etc. Alright, so we do that. And so if we draw the graph of this function, we will see that right, so when we draw, right, and we find that Alright, so you see that this function defined on the whole real line here means that every point has a function value, okay? And this one is periodic function. So the period can be pi or 2 pi or 3 pi, right? There's a lot of period because if you put p to be equal to 2 pi, means that this is a period, right? So 2 pi period here, from here, here, this is a period. You can see that the graph of the function repeats itself, right? Repeats itself. But the smallest period for this function, for this periodic function is what? It's just pi. Okay? So, so f of x is period. Say pi, 2 pi, 3 pi, right? A lot of period. And its fundamental period is just pi. Okay? So this is a very simple example. So there are many periodic functions, especially in trigonometry, right? In trigonometry, you know the sine function, the cosine function. So that with observation, 1 cosine x, sine x, right? Sine 2x, sine 2x, okay? Etc. Cosine nx, sine nx. A lot of sinusoidal functions. So these functions are periodic functions. Okay, so they are periodic functions. With period 2 pi. Okay? So every function, so you can regard the constant function as a periodic function with period 2 pi. Actually, the constant function has period p, or p could be any positive number, right? So you can say that it's a periodic function with a period of say 0.5. This is a periodic function of period 3 times 3.7. right? So any part number p can be a period function of a constant. Okay, and you know cosine has period 2 pi, 4 pi, 6 pi, right? Now, how about sine 2x? Sine 2x has period pi, 2 pi, 3 pi, right? So a lot of, but they have a common period. What is the common period for all these periodic functions? 2 pi, right? So you can select 2 pi to be the common period of these periodic functions. Right? Now, so this function, we call they form the so-called, right? The so-called trigonometric system. Right? So whenever we talk about trigonometric system, we are talking about that the set of all these periodic functions. So the system is just a collection or the set of all these functions. And they will play an important role in Fourier analysis. Okay, so now I give a simple theorem. Talk about the so-called orthogonality of the trigonometric system. Right, this is what orthogonality. Right, the first thing is about if we integrate, so actually it's 1 times cosine in x. Okay. So the product of the constant function with the cosine function and integrate over one period 2 pi, okay, is equal to 0, and this is the same if you consider the constant function 1 times this the sine function. Okay. Right. And this is a very simple result from calculus. You know how to find the definite integral of the cosine function. Okay. So because we integrate over one period, and the cosine function, as we know, cosine function, if we integrate one period, so if we integrate over one period, the area, as we know the area, so we have positive area here, but we have negative area here, and they cancel each other, right? So that this is cosine x. So this is the graph of cosine x, and you know that. Okay, so you know how to evaluate the definite integral by using the antiderivative of the sinusoidal function. So the antiderivative of cosine function is sine function, right? And the antiderivative of sine function is just the cosine function. All right, so you know that from calculus, and we consider the product of two different cosine functions in the system. So we have nm. Right, this is also equal to 0. And for sine function, for different sine function, here, okay, it's equal to 0 for all n not equal to m. And how about the product of cosine and the sine? So for cosine mx and the sine mx dx is equal to 0 for all n equal to 1. Alright, so we have 3 points, right? So this is the talk about any kind of situation that when you pick up one member from the trigonometric system and pick another member and you take the product and integrate over one period, they're all equal to 0. Okay? So it's called orthogonality. It's called orthogonality here. And the proof is quite simple. Okay, we use the sum and the difference identities in trigonometry. Okay. Right? So what are sum and difference identity? We know that cosine nx, cosine mx actually is equal to one half of sine minus mx plus cosine times m. Okay. So this is called a sum identity, right? And we know sine So in the mixed type, okay. Right, so you have the identities here. Right, and again, you apply the first one, right? Because this is the pure cosine function. So when you integrate over one period to pi, it is equal to 0. And when you integrate this cosine function for one period, it's equal to 0. Okay, so that's why this is equal to 0. Okay. And the same for this one and for this one. Right, so that is simple. So any questions about the orthogonality of the trigonometric system? So they are quite simple, right? Yes. Alright, so now if we want to construct, so how to construct a periodic function with period to pi. If you have a question like this one, that you want to construct an arbitrary periodic function with period to pi, so you can try the trigonometric system. So that the partial answer is that a trigonometric series A0 plus A1 cosine x plus B1 sin x plus A2 cosine 2x plus B2 sin 2x plus capital plus an sin nx Alright, so this is an infinite series, right? An infinite series. So basically, it's a linear combination of functions in the trigonometric system. Okay, the functions. So this is just a linear combination, but actually it's an infinite. So it's a series, right? Because you have many terms here. So in shorthand notation, we can write this as A0 plus summation okay, so this is an infinite series. Alright, so to consider a trigonometric series. And where A0, A1, B1, A2, B2, etc., AN, BN are constants. So this trigonometric series will be a periodic function with period to pi, okay, under a condition that if the periods converges for all x in all. Okay? Alright. So for each x in R, if you substitute a particular value for x here, this has become to a series, numerical series, right? Because you have many terms of real numbers together. Alright, so if you fix an x here, it becomes a series. And then you have to know whether the series converges or not. Okay? If it does, so here, so if the series converges for all x in R, then it's very easy to see that this becomes to a function and with period pi, so it's become to a periodic function. Okay. So trigonometric system, all right, can be used to construct an arbitrary periodic function with period to pi. Okay. This is one direction. So if it's converged, right? But the question related is here, can a periodic function f with period to pi be expressed as a trigonometric series. Like that, i.e. f of x can be written as a0 plus this infinite series for all x and r for some a0, a1, b1. So this is the question. Right? There are two different questions, right? The first question is that we can use the trigonometric system to construct an arbitrary periodic function. Okay? If the series converges for all x and r. So of course, if you assign arbitrary constants here to form a trigonometric series, right? We don't know whether the series converges or not. We don't know in general. Okay, but if you do, can prove if you can prove that this trigonometric series converge, then it can becomes to a periodic function with period. The other question is that suppose we have a periodic function, suppose with period 2π. Can we express this periodic function as a trigonometric series? Okay, so it is later on we will see that it is a so-called representation theorem. Okay, so this is the question mark. And the first thing, so we try to answer this question. Right? And then, so we want to know that if this is true, then the coefficients here, A0, A1, A2, A3, A1, B1, A2, B2, this coefficient must be related to the original function of x, if this representation is true. So to answer this question, we first derive necessary condition for the positive answer. So we want to derive the necessary conditions. So we want to know that what is the necessary condition for a periodic function of period P2π to be represented by a trigonometric series. Okay, so what is the necessary condition? All right, so we assume that this periodic function can be represented by certain trigonometric series. So we assume this is true. Okay? And this is true for almost all x and r. Okay? So I will explain later what do we mean for almost all x and r. So, i.e., the partial sum function right? So I believe you have studied series of functions in calculus, so that for the partial sum function, is say xm, x defined to be a0. Okay, so then this is the so-called partial sum, because we just take the first m plus 1 terms together. Actually, it's the first 2m plus 1, because including a0, a1 cosine x, b1 sin x up to am cosine mx, and the bm sin mx. So this is the so-called the partial sum function. And this is a well-defined function because it's just a finite linear combination of the sinusoidal functions. Alright, so the partial sum functions, okay? Converges, right? Converges to f of x as m goes to infinity for almost all x. Okay, so let me remark. We let n be a set of such that the xm does not converge to f of x. Right. So we collect all the point x such that for any of that x, right, the partial sum, this one, does not converge to this function value. We collect them together, right? Then we say that converges to f of x for almost all x in R if the length of n is 0. So if the length of n is 0. Because that n is a subset of the real line. So you can measure the length of this subset. Okay, you will measure the length. And if the length of n is 0, then it means that if this set is not significant. Okay? So we use a terminology called that actually the partial sum function converges to the function value for almost all. Right? So every time when we talk about the concept of for almost all, it will mean that that for the exceptions, right, the collection of all exception points together, then this collection, this set has 0 length. And so we further assume that the function defined by taking x value of each term so if we first assume that converge for almost all x in R. So that means that essentially this infinite series converge essentially for all x in R. So we allow that some point of x, this series has sum equal to infinity because every term is positive, right now negative. But it's possible when you add up them together, it becomes to infinite. It's possible. Okay, so we allow for that possibility, but g of x become to infinity, right? For some x, right? And we collect all those x together, then the length of this n. Again, we can define n as the point of such that the value is infinite. Okay? And the length of this subset n becomes to 0. Okay? Then, so it is not essential. So we say that it is almost all. And the second thing is that the g of x is finite. Because that can be infinite, but it's infinite on a subset of R such that the length equals to 0. So that if you tap with the length, then the product is also 0. So it will not affect the evaluation of the integration. Okay? So that so we assume that the integral is also finite over one period. Okay, this is a sufficient condition is that if we know the coefficients, the absolute value of coefficients, right, sum together, and the sum is finite, then of course that 1 and 2 are true. If we know that this quantity is less than or equal to an, because the cosine function, the absolute value of cosine function is less than or equal to 1. The maximum value of cosine function is 1. So this term is less than or equal to an, and this term is less than or equal to an. So if this series converges, then of course g of x is finite for every x, okay? And has upper bound. So actually this is implies that g of x is less than or equal to a0 plus summation okay, for all x. So if this is true, then g of x is upper bounded by this term, by this quantity, and it's finite, right? So it has an upper bound. And because this has an upper bound, so the integration, so in this one, so suppose the upper bound is equal to, we say that this is equal to m. Alright, so suppose this is equal to m, so this is m. Okay. So the value, so the integral has an upper bound which is 2 pi m. So of course, this integral is finite. So this is a simple sufficient condition to guarantee 1 and 2. Right? It's very simple conditions to guarantee 1 and 2. Any questions? So our purpose is to derive some necessary conditions. So that we assume that f of x can be represented by such a trigonometric series. And the meaning for this one is here. The partial sum function converges to this function value x for almost all the x in the real one. And so, okay. And we also further assume 1 and 2. Okay, so now, all right, so we have the partial sum function. The partial sum function. Okay. When we take the absolute value, will be less than or equal to a0 plus summation. Okay, so we take the absolute value here. So this is the absolute value here, and we know that it's upper bounded by this sum. Okay, and this is just then equal to 3x. Right, and we define g of x here, include all the terms, infinite many terms. Right. So of course the finite sum is less than or equal to g of x. Because every term here, every term here is positive. So we have fun. Okay, so this is true for every partial sum functions. Alright? Then this implies, so this implies that the integral, the absolute value of the function when integrate over one period is finite, i.e. f is absolutely, because we take the absolute value, integrable. Because this integral is finite, so it's called f is absolutely integrable over a period from 2 pi to pi. Okay? Over, sorry. Alright. So this is called absolutely integrable if this integral is finite. Okay. So this will imply 1. Second, it will imply so that we can compute this integral without the absolute value sum. Just because that if the absolute value, all right, of the function is equal, it implies that this integral exists. Finally. Okay. So now we already assume that the partial sum function will converge to f of x. So f of x actually is the limit of x, the partial sum function, right? So f of x is this one. Now, because of this property, because of this one, and this property, this 2, right? We can exchange the integration and the negative process. Okay? It's guaranteed by the so-called, so I give the reason, by the dominated convergence theorem. I know that some of your professors just say, okay, just exchange them. Okay, it's fine, just fine, okay. But sometimes it's fine, sometimes it's not fine, okay? It depends. Okay, it depends. So here I can exchange the integration because integration is a limiting process. Integral is just a limit of the sum, Riemann sum, right? When you learn integration in calculus, you first form a Riemann sum and then take the division as final as possible, and in the limit, the Riemann sum becomes the Riemann integral. So integration is a limiting process. Right? So now you have, in here you have a limiting process and outside a limiting process. If you want to exchange two limiting processes, you have to be cautious. Okay? Sometimes it's fine, sometimes it's incorrect. Okay? But here, we use the so-called dominated convergence theorem. So we are safe here. We can exchange them. Okay? We can exchange them. And when we exchange them, we find that because the partial sum function here is just a finite linear combination of the sinusoidal function, right? And so by linearity of integral, right? So you can see that because this is A0 plus summation. So this is limit. Alright, so now you have A0 dx. And you have An plus Bn okay, that by linearity of integral. Okay, so you have the integration of a linear combination of functions is equal to the same linear combination of the integral of individual functions. So that is the linearity of integrals. Okay, and now we apply the orthogonality of the trigonometric system. This integral is equal to 0, right? And the same, this integral is also equal to 0. So this sum vanished. vanished. And so finally, we have limit and go to infinity, and with only one term left. Okay? And this term does not depend on any m. Oh, sorry, this is m. Because this term here vanish, right? They all become to 0. So we have this one, and this is a constant. So the limit of a constant is equal to this constant, so this is 2 pi. Okay? Alright, so this is, so from the second part here, we prove that. So we prove the A0 can be obtained from f of x by this integral. Alright, this is the second necessary conditions. The first necessary conditions here is that the x value of f of x is integrable. Okay, it's integrable. Because we are going to find some necessary conditions, right? For this to be true. Okay? And we find that if this is true, and we further assume both condition, then we have that the function, this function f of x, must be absolutely integrable over one period. This is necessary. The second thing is that the A0 here, the A0, this term, right, must be equal to this integral. No other way around, okay? This is necessary. The A0 should be 1 over 2 pi times the integral of f of x over one period. This is the second necessary condition. Right? And so, and then we have quite a few more necessary conditions to go. We have to take a rest. So, yeah, okay, so let's take a break here for 10 minutes.